So last videos, my microphone was turned off. I apologize for that. Let us go through those slides, maybe a little bit faster, that since you had the opportunity to read them yourselves. The idea is I want to use integrals to find the volume of a region rather than just the area on the Cartesian plane. Now, in order to do that, it's helpful to refresh on certain volume formulas, and we will be using those volume formulas to, build up the larger and more complicated solids. So very classical, we have a circular cylinder where the base of my cylinder is a circle of radius lowercase r, and the height of this cylinder is h. Then I know my volume is going to be pi times r squared times h. More generally, we still use the word cylinder to mean some flat region, which I then project up a distance of h units and have an exact copy of that same region sitting above it. The volume in between is going to be the area of my region, here it's labeled B2, times the height. So if I had a circular cylinder, or more commonly known as a cylinder, this would be my pi r squared h, but I can do this for other shapes as well, other bases besides just circles. So that'll be handy. That'll be very handy as we move forward in this lecture. The other common region I want to talk about is just a rectangular box whose dimensions are, let's say, length L, width W, and height H. Then the volume of this solid is going to be volume V equals L, W, H. Excuse me. So again, these should be very common formulas that we recognize from years past. Maybe haven't used them in a while, but these should be familiar. Now, the problem we want to address here is finding volumes of solids that aren't so nice. So here I have a very horrible looking loaf of bread. It's blue, it's sort of risen unevenly in the middle there. The claim is that we can solve for the area of this solid using calculus. So my idea here is that this solid is sitting above the x-axis. So any coordinate x I can slice, and I'll ask, what is the area contained inside this slice? So where does the solid meet this plane? So again, keeping this loaf of bread analogy, I have my knife, I can just drop straight into it, and on my loaf, I'm asking, what is the surface area exactly at the position I have sliced? Now, this amount of area is going to be different for different x coordinates. So in this picture, if I took x more to the left, I should be getting a smaller surface area for that slice. If I took x more to the right, perhaps again, I'd get a smaller surface area. It seems that the largest surface area is exactly where they have drawn this figure in. So this is a function that I will call a of x. Give me the coordinate x. The function a tells us what the surface area is there. We're going to use this area function to build up, well, what else would it be but a Riemann sum. So in this diagram on the left, I have that horrible looking loaf of bread again. And on the right diagram, I am approximating my loaf of bread with slices. And I claim that the volume of each of these slices is something we can compute. So at each slice here, it looks a bit odd because I've lost my smooth top, my smooth shape to this loaf. What is going on is that we have just assumed that the slice is the same shape the whole way through. So this slide is calling these slabs. It looks like I just stacked up a bunch of slices of toast together that came from different loaves of bread. If you're going to be, fanciful about it. So let's calculate the volume of my approximation and see about making it the best approximation it can be.